In this video, we're going to start with our simulation that we had in a previous example, where we were looking at a cooling of the hot end in a 3D printer. Only this time, we're actually going to use the control feature. We're actually going to turn on a switch in the system, which is going to let some, current flow through a heating element and act to heat up the heating element. To make this interesting in the sense of seeing the contrast between control and no control, what we're going to do is start off at a temperature of 5 degrees above the equilibrium. And then what we're going to do is set the control not to 0 the whole time. That's what we did before. What we're going to do this time is use an external control that's 0 initially. And so we should be able to predict in our minds, okay, so things are going to start at 5 degrees and then cool down over time. But after 4 seconds, we're going to turn on the heater, and that should start the hot end heating up again. And we're going to need some details there about how big that control is. We're going to keep it simple and sort of mathematical, less physicsy. We're going to make it 1, but we're going to use a multiplier here of 10. So if you think of like, this is the current that's going through the heater, and then we convert the current to the actual units of here, degrees Celsius per second, through this B value. So we're going to use a B value of 10 there. So what we're going to do is walk through how that works in relation to what we did before. The first thing we're going to need to do is define a number of different parameters that relate to the control. So what I've called this is U on time, which is when the U turns on. Seemed like a compact way to say that. The other values, the K simulation time and X naught, are the same as before. And we also have our B multiplier value, again, going back to the on paper work, which should be always closely associated in your mind with what's showing up in the code. All right, so we take a look at what we had in the previous example. We had to, for our first representation of this, we did a simulation based on a first order model just representing the derivative. So we had to define a function that computed the derivative as a function of time. And so we're going to put that in here. And what we see immediately is that this model that we had before is missing the control part. So there's no plus U in there. So here we're going to take a step and actually do this what I think is the correct way, which is to represent this model actually as a function of several things here. If we take a look at our model, it's not just X and T. In fact, we should probably put K in here as well. The fact that K is defined earlier lets it kind of slide into these functions, but it's good practice to actually define these values in the input to our function, so there's no confusion. And what we're going to do with those, now we have K, we have X, then we want to do minus B times, and what I'm going to do here is make UF a function. So if you think back to when you learned these models in a previous class, this function gets called over and over and over again, and it tells you, okay, I'm at temperature 5 and my time is 0. What's my rate of change? This is the question this function has to answer. It doesn't do any simulation, it just says, if you tell me what the temperature is now and what time it is, I'll tell you what dx dt is, what the rate of change is. What we're including here is UF, which is a function, and let's actually define that so it's really clear. We're going to define UF as a function of time, and it's a simple if statement. So if our time is less than the U on time, then we return 0. Otherwise, we return 1. So the idea is if someone comes up and says, well, it's 3.5 seconds into the simulation, well, that's still less than the 4 time when we turn on our switch. So our control, our action on the system is going to be 0. We're not doing anything yet. Whereas once we get past that 4 seconds, so if time comes in here at 4.5 seconds, that's bigger than 4. So yes, the control is on. So we're going to have a control on. We're going to have a 1 value here, and so it should be a plus. And so we're going to add that to our rate of change. We're actually have the heater turning on. It's going to increase the, it's going to give us a positive influence on the rate of change of the temperature. And so, yeah, I think that pretty much does what we want. The challenge is going to be incorporating these into the syntax for the model that we used. So everything else here is pretty close to right. So in fact, we're going to grab everything here. We can try running it if we want. We're going to have a failure. All sorts of errors. The main one being that the DE model is missing 3 required positional arguments. Oh, okay. No kidding. We didn't define what K, B, and UF were and how they fit into this. Fortunately, the syntax for the ODE int function is flexible you just add an extra arguments thing here. And it's a bit odd. Use the round brackets here, not square or curly. So round brackets for a composition. There's some funky technical term in Python. But the key thing is you just list off the things that you want. So the 3 extra things, x and t have to go. We can't do a differential equation model without them. But the other 3 that we need are k, b, and uf. And just a note, if you ever just need one of these, you just put k comma as opposed to leaving it as is. But I think this should do it. Let's give it a run. Ah, perfect. So what you can see here is that we started at 5 degrees and we're cooling until we hit 4 degrees, and then all of a sudden we turned on the heating element and things started getting higher and higher and higher for the temperature because we were actively heating the system. So by having this term in our simulation, we get to have things increase over time. So this is the behavior we expect when we have natural cooling for a while and then we flip the switch and start heating it up. And the question is, can we then repeat this using our other models for this system? And the answer, of course, is yes, but let's look at all the technical details that come up with that. So previously we did the same model with a state space model. And again, the state space model requires 4 matrices, A, B, C, and D, filling out these ingredients here. And we actually had most of these before, so we're going to copy these verbatim. And then we're just going to look and see what changed. So we only changed the control this time. So the one thing we have to do is change our B matrix here. And remember, this is the actual simulation of the system here. We don't mess around with, or sorry, we do change that. The Y here is what we don't really do much with at this point. It's the observability thing. You'll see way more of this in control theory. We want just our Y equal to X. So there is no change to this other thing involving U. We can have a discussion about that if you like sometime. The thing that we also need, though, is a matching set of U values, which are the control's output at each time t. And so if we take a look at the input here, before we had a U vector that was all zeros. We built it here. Now we have to have it built as zeros up to 4 seconds and then 1 afterwards. But fortunately, we have some lovely syntax for this. So this is the all 0 to start. And then here we're going to say, well, whenever t is greater than or equal to, let's make sure we got the same thing. Yeah, it's greater than or equal to, there's actually u on time. U on time. We are going to get a value of 1. So what is this doing? Identify all the times that are past 4 seconds or equal to 4 seconds, and make the control value there 1, because we're setting the u at those indices equal to 1. In fact, let's actually add an extra plot here of t against u, just to see what we should get is flat 0, jump up to 1, stay at 1 for the remaining time. And of course we have a typo here. Ah, right, we just changed this to t state, so this should also be t state to make the plot work. Our t had another value earlier. All right, oh, in fact, we got ahead of ourselves here. That actually all worked. So let's just comment out these plots here for a second. This is our step function for the U thing, for our control. We leave the voltage 0 or current at 0, and then we spike it up to 1, and it keeps going from there. And that's exactly what we want, so we can turn that plot off. And then we can go back to these results here, and we see exactly what we saw in the previous graph, which was a cooling down until we turned the heater on, and then it increased from there. All right, last but not least, we're going to do the same thing, but based on our Laplace transform function. The nice thing about this, again, is that the analysis is all about, the system is all about this transfer function, and it stays exactly the same. What we're going to be changing is the U function, and in fact this is going to be exactly the same kind of construction we just did. We're going to just mix and match what we did before. So let's go here, and we're going to build our transfer function, which is the system. And then when we come to do the simulation, we just have to remember to rebuild our U for this one. So in fact, let's call this U transfer. And we're going to do the same thing we did here. Oops, no, this part here. This is the part we need. U transfers that, and then we update it with T transfer, and so on. Perfect. Let's just try to plot that to make sure we actually have matching indices. We'll need to fix something here a second. Actually, yeah, let's comment all that out. And we'll plot T transfer, and so just So recognize that should be U transfer. And of course, toss undefined, T, and U transfer. Perfect. So again, just reminding yourself, these are dots, like these are not actually a continuous function, but we have a bunch of dots that are 0, and then the U turns into 1 values after a while, corresponding to that transition after 4 seconds. Just comment it out. Now, just gotta be careful here that we use U transfer for this particular model. And then I think we're good to go. Let's give it a shot. Oh, that's interesting. That is not the same graph we got before. If we take a look up here, these all start at 5 and cooled down, then heated up. They heated up to like 35. If you take a look here, it's not cooling up as much, or it's not heating up as much. Now, if I think about that for a second, in this model representation, we just had the transfer function, but the b times u of s, actually, we only ever told it about u. There's no chance to put a b in yet. If we go up to the state space version, we actually said, no, there is a multiplier called b, and the one above that, we had the multiplier b. So here it's a little more DIY. Instead of just using u transfer, we have to put the b in ourselves to be able to account for that translation between, say, current and the actual impact on the heat change. And when we do that, poof, we're into the same realm. So what we're going to do is plot all 3 of those again to compare. I'll grab those from our previous answer. And sure enough, here are the 3 graphs, basically on top of each other again. And so all 3 models are representing the same function with the little technical caveats that we discovered along the way. But the key thing is we can now model what would happen if we turned on our heater at a certain time. And if we quantify that further, we could say how much heat do we need to be adding to achieve a certain goal, which would be getting us into the introductory control theory aspects, where we want to achieve a certain behavior out of the system. For now, it's just enough to know that we can exhibit the natural behavior and then activate something and see what the impact of that activation is on the updated system.